All right, today we are introducing telescopes and light and energy. This is all chapter 27, and the very first section of chapter 27 talks about how we gather information about things that are not on our planet. So for the next 3 weeks, we're going to be talking about a little bit about outer space, seasons, tides, moon phases, kind of those things that are close to us, but not necessarily directly on our planet. So section 1 starts with how do we learn about those things that are not on our planet, and one of those main things that we use is telescopes. So we're going over the basics of telescopes, different kinds, and how they work. There are two things that we use telescopes for, or two ways that they help us learn about things that are not on our planet. First, telescopes can gather more light than just the naked eye. They can do that because they have a bigger lens than your eye. So they gather more light than your eye. The more light you can gather, the better you'll be able to see. The second thing that a telescope does is magnifies the image. It makes the image that you're looking at bigger. And that also makes it easier to see. So traditional telescopes help astronomers in two ways. They gather more light than your eye can gather by itself, and they magnify or make images bigger. If you're choosing a location for a telescope, especially a large telescope like the one in the picture, if this is going to be a permanent installation, like scientists are actually going to use this telescope to take real data, you want to carefully think about where you would put that telescope. The closer you can get to what you're looking at, the better. So you might want to put your telescope on top of a mountain. That also reduces the amount of our atmosphere that you have to look through, which would help reduce having to look through things like pollution. The top of a mountain isn't going to have as much of that, and you'd be closer to what you wanted to see. So because of thinner air and high elevations, closer to what you want to see, less atmosphere to look through, a mountain peak might be a good place to put a telescope. Most telescopes are located in desert climates for a couple of reasons. If you're trying to look at the sky, you probably don't want to put a telescope in a rainforest because it rains all the time, cloudy skies. If you want to be able to use that telescope as many nights out of the year as possible, you try to pick a place where you don't get very many clouds. A desert doesn't have very much rain, not very many nights that you would miss because of clouds. Skies are clear and the weather is dry. It also helps so that you don't have to close up to keep your telescope from getting wet. You don't have to worry as much about the dew collecting on the telescope. Third, you don't want to put your telescope in the middle of a city. If you have lots of other lights around you, it will be next to impossible to see anything through your telescope. It's called light pollution. So you would want to put your telescope somewhere in a remote area where there aren't a lot of other buildings or street lights or lights from people. You have a question, Jared?
Isn't that why it's better to stargaze in rural areas?
Yeah, absolutely. Like they've been suggesting recently, if you want to see the northern lights, try to get away from cities and towns. Because if there's light pollution, you can't see the things in outer space nearly as well. So choose a remote area because there's no city lights. Mountain peaks, desert climates, remote areas. So how do telescopes work? We need to know a little bit about the different kinds of telescopes that there are. When you think of a traditional telescope, you're probably thinking of an optical telescope. That would be one that you can look through, and it would use either lenses or mirrors or both to gather and focus the light. Might be from a star, might be from a planet, could be from the moon. Light reflecting off of a planet and the moon. A traditional optical telescope uses lenses or mirrors to gather and focus the light. Optical telescopes are usually kept in domes, like the one we saw on the previous slide. That is, of course, to protect it from the weather. Usually those domes are able to rotate so that you can turn the telescope in any direction and look at all different things around you in the night sky. The amount of light that they can gather depends on the area or the size of the lens or the mirror that the telescope is using. The larger the lens or the mirror, the more light you can gather. The farther away you're going to be able to see things, or the better you'll be able to see things. Within optical telescopes, there are two kinds: refracting telescopes and reflecting telescopes. Refracting telescopes use two lenses to focus the light. One of them is called the objective lens. The objective is always at the end of the telescope that's away from your eye. The purpose of the objective lens is to gather the light and bend it to form an image at the other end of the scope. It gathers the light and bends it to make an image at the other end. The other lens is called the eyepiece lens. As you would expect, this is the one that's right next to your eye when you're looking through a telescope. The purpose of the eyepiece lens is to magnify the image. So the optical lens, or the objective lens, makes the image. The eyepiece lens makes it bigger. This is the kind of telescope that you will actually get to use tomorrow and Thursday when we do our lab. Most large refracting telescopes were built before 1900. This is the older of the two kinds of telescopes, or optical telescopes. This is the older technology. So most of these large refracting telescopes are getting up there. There's one at the University of Illinois in Urbana-Champaign. It was built in 1896. Still works, though, by the way. You don't have this picture in your notes, but just to give you an idea of how these work, you've got the eyepiece lens here. This is the one you would look through. This makes the image bigger. The objective lens is down at the other end. This is the larger of the two lenses. It takes the light in, bends the direction of the light so that it comes to a focal point, and that helps to make the image that you see with your eye. And then the eyepiece lens makes that image bigger. One thing we're going to look at with your lab is the focal length of each of those lenses. So that would be the distance from the focal point to the lens. Each lens has its own focal length. So why are large refracting telescopes sort of falling out of favor? Why were most of them built before 1900 and not so much after that? Large refractors are very difficult to construct because you have to have a large lens. The light has to pass through a lens. Lenses are made of glass. The glass that you use for a lens has to be perfect. No bubbles, no cracks. It's got to have the exact right curvature, how much it's rounded on the outside. If you don't get that degree of curvature right, you're not going to get to see the image that you want. It might be blurry. Another problem is that lenses can only be supported at the edges. If you think about a pair of eyeglasses, there's rims around the outside, but you can't put a support in the middle because you wouldn't be able to see through them as well. So with just rims or supports around the edges, that makes it harder to build them larger, just because they're so heavy and large. One thing that's kind of interesting is that glass is what's called an amorphous solid. That means it doesn't have a orderly arrangement of atoms. The atoms in glass are not arranged in nice, neat little rows. They're just kind of randomly arranged and stuck together, which gives glass a couple of interesting properties. It tends to act more like a fluid in some senses than it does like a solid. Old lenses, very old lenses, will have glass that has started to flow or sag in the middle, and that blurs the image. I've never tested it, but I've been told if you take a window from a really old house and you measure the thickness of the window at the top and the thickness of the window at the bottom, that it will be just slightly thicker at the bottom than it is at the top, because glass still kind of flows. Even though it feels like a solid, you can tap it and you think it's a solid. But because it's an amorphous solid, it does have that ability to flow a little more like a liquid. Second kind of optical telescopes are called reflecting telescopes. These are the ones that people tend to have in their backyard. If they're an amateur astronomer and they've bought a telescope for a couple $100, it's usually a reflecting telescope. Reflecting telescopes have one large curved mirror to gather and focus the light instead of a lens. The large mirror is still called the objective. It also has a secondary mirror to reflect the image to the observer. You have to have a secondary mirror because if you think about putting a mirror down at the end of the telescope, can you see through a mirror? No. So you have to have another mirror to reflect that image to your eye. And then it does still have an eyepiece lens. The eyepiece lens is the one that's right next to the part that you're looking through, and the purpose of it is to magnify the image. And again, you don't have this picture in your notes, but just so you can get an idea, this is what a reflecting telescope would look like. Notice that the eyepiece is off to the side here instead of at the end. You have the objective, which is the primary mirror here. It's the larger one. So the light comes in an opening at one end, goes down to the primary mirror, gets reflected up to the secondary mirror, which is right here, and then out the eyepiece to your eye. So the primary mirror collects the light, the secondary mirror sends it out to your eye, the eyepiece lens magnifies the image. Third kind of telescope is called a radio telescope. You might be able to guess that instead of collecting light waves, it collects radio waves. Objects in space, like stars, produce energy in all different parts of the spectrum. They produce light, but they also produce different kinds of energy, like radio waves. So you can take those radio waves that are produced. Usually they end up using a computer to turn it into kind of like an image or something that they can study. And you can learn about objects in space with radio waves too. A couple of advantages to radio telescopes is that radio waves can pass through the clouds, so you don't have to worry about the weather. And it can pass through the clouds of dust between the stars. So any sort of dust, pollution, anything in the atmosphere that light rays cannot pass through, radio waves usually can. Another nice thing about radio telescopes, especially for the astronomers, is that they can be used during the day. So you can work normal business hours like everybody else instead of having to stay up every night. Radio telescopes look a lot like the satellite dishes that are used for TV, but they're quite a bit larger. Radio telescopes have a dish, usually kind of semicircle shaped. The radio waves come in. They are, yeah, it does. It looks exactly like your DirecTV receiver, but it's much, much larger. They're collected. The dish reflects them back to a receiver, and the receiver is usually mounted at the focal point of that curve. So the waves come in, they're reflected off the curve back to the receiver. The receiver, and then usually some computers along with it, are able to collect those signals and turn them into something that we can interpret, like a picture or a different data set. These are usually made of solid metal or a wire kind of mesh, something that's going to collect radio waves. That metal or the mesh is what collects and focuses the radio waves. Perhaps one disadvantage to radio telescopes is that radio waves have much longer wavelengths than light waves. So that means that radio telescopes have to be bigger than an optical telescope. Here's where we're going to switch papers. So you should have one pretty much filled out at this point. Switch to the other one. The next thing that we're going to talk about just for a little bit are some basics of light energy. What do we need to know about light to be able to understand telescopes and gathering information about outer space? One of the things that we might be looking at or studying in outer space are stars. We know, of course, that stars emit light. They emit light that we can see. They also emit energy that we cannot see. You can't see radio waves. We already talked about telescopes that use those. You can't see ultraviolet light. You can't see infrared light. There's lots of energy that is being emitted by objects in space that you can't see, as well as the stuff that you can see. Electromagnetic energy, which is the stuff that's produced by stars and different objects in space, includes lots of different kinds of energy. Light, X-rays, radio waves, microwaves, gamma rays, cosmic rays. Lots of different kinds of energy fall under this spectrum of electromagnetic energy. Each type of energy on this spectrum has a different frequency and a different wavelength. You might know what frequency is if you are familiar with talking about different sounds. Different sounds have different frequencies. Frequency and wavelength are two things that you can measure about any kind of wave. Light waves, sound waves, even ocean waves. You could measure a frequency and a wavelength. Each type of energy has a different frequency and a different wavelength, but all types of electromagnetic energy have the same velocity. That's how fast they move from one place to another. 300,000 kilometers per second. That would be light speed. How do we describe these different types of energy? Energy travels in waves. So we can describe or measure the frequency, which is the number of waves that pass by a point in 1 second. If you could stand on the beach and count how many ocean waves hit you in a given amount of time, you could translate that into a frequency. Wavelength is the distance from peak to peak. So from the top of one wave to the top of the next, or from trough to trough, which is the bottom of one wave to the bottom of the next. Frequency and wavelength are inversely related. So that means as one goes up, the other goes down. If the frequency is high, the wavelength is low. If the wavelength is high, the frequency is low. They are inversely related. So if you look at this picture, remember frequency is the number of waves. Wavelength is the distance between them. Which one has the highest frequency or the highest number of waves? 2, the second one. Which one has the highest wavelength? 3. Frequency and wavelength are inversely related. 2 has the highest frequency and the shortest wavelength. 3 has the highest wavelength and the smallest frequency. One thing that you will see in your book is a picture of the electromagnetic spectrum. This is the range of wavelengths and types of energy from radio waves all the way to gamma rays. So you'll see another picture of this in your book. We've got things that have a very short wavelength, like gamma rays, all the way down to things that have longer wavelengths, like AM radio. Notice that visible light, the part of the spectrum that we can see, is this tiny little sliver right in the middle. We cannot see very much energy that is produced at all. We can only see visible light. It's this tiny little spot. One thing that's interesting about visible light, notice down here, each color has its own wavelength. Each color has its own frequency. That makes for some very interesting properties about light and color. Remember, the visible spectrum is the range of wavelengths of energy that we can see. Not very much. It's a very small slice of all the energy that's produced. And each color of the rainbow has its own wavelength and frequency. If you put all of the colors together, then of course you get visible light, or what we call white light. We've got just a couple things to talk about here. Of all of the colors, red has the longest wavelength. What makes that interesting is that it is bent the least when you pass it through a lens or through a prism. So one thing that I wanted to show you, which is not on your notes, is this picture. When you take white light or light from the sun and you send it through a prism bends or refracts the light so that you see each of the colors on the other side. You see each of the colors because the prism is separating the colors by frequency. That means it also separates by wavelength. Red has the longest wavelength, so it's bent the least. Violet or purple has the shortest wavelength, so it's bent the most. What's cool about this is that this has applications in everyday life. What's the most important road sign on the road?
Stop sign.
Probably a stop sign,
Yield sign.
which is red. What signs are orange? Construction. Don't hit the workers. What signs are yellow?
Purple.
Warning signs. School zones. Pedestrians. What's green?
Roadway.
Go. Go, but
And
also like on the interstate. It's
Travel sign.
exit.
Directory sign.
On the interstate, what's blue? Food. Yeah, those are blue as well. Food, hotels, lodging. So the least important road signs for you to see are the color. Listen. The least important road signs for you to see are the color that gets interfered with the most. The most important road signs for you to see are the color that gets interfered with the least. And I think that's kind of interesting. We will quit there for today.
Are these? What am I saying?
Yes.